Just imagine, what if we weren't alone in the universe? What if the answer to that question was just around the corner, a mere 4.37 light-years from our planet? Welcome to the fascinating and mysterious universe of Alpha Centauri, the star system closest to our Sun. For centuries, this bright star in the night sky has captured the imagination of astronomers, scientists, and dreamers the world over. But what really lies hidden in the depths of this star system? From unexplained radio signals to disturbing observations, Alpha Centauri has never ceased to intrigue and thrill. Dear traveler, welcome. Today we're diving deep into the mysteries surrounding this cosmic neighbor, exploring the boldest theories and most astounding discoveries. But before we set off on an adventure beyond the borders of our solar system, where the unknown reigns supreme, remember to like the video and subscribe to the channel so you don't miss a thing. Thank you, and have a great trip! If you're in a country below latitude 29 degrees north, such as Peru, Egypt, or Thailand, you've probably already seen one of the brightest stars in the southern sky. After our Sun, Sirius, and Canopus, Alpha Centauri A is the fourth brightest star in our night sky. However, due to its location in the constellation Centauri, it is only visible from Earth in the southern hemisphere, and then only on clear starry nights. Located in the Milky Way, it is framed by the constellation Scorpio to the west and Argo to the east, just above the Southern Cross constellation, known for its rich star cluster. While the first observation of Alpha Centauri was recorded during the 2nd century, its binary nature was not established until 1689. Alpha Centauri AB was then the second binary star to be detected. Then, in 1915, a third star named Alpha Centauri C, or more commonly, Proxima Centauri, was discovered. Although relatively distant, its own motion on the celestial vault was extraordinarily similar to that of the other two stars. This confirmed that Alpha Centauri is a triple star system and not a double one as previously observed. If detection of this system was possible as early as the beginning of the 20th century, despite technology still in its infancy, it's because it's the closest star to our Sun. Indeed, the Alpha Centauri system is only 4.37 light-years away from our own, which, on the scale of our vast universe, proves prodigiously close. Of the three stellar elements making up the system, Proxima Centauri is the shortest distance away, at 4.2 light-years. However, while this triple system takes third place in terms of brightness in our starry sky, the Proxima star remains invisible to the naked eye. Let's get up close and personal with this fabulous trio and find out more. Alpha Centauri A and B form the main binary star. These two stars, which shine brightly like our Sun and bear a striking resemblance to it, are easy to spot. More traditional names have been attributed to these stars, depending on their location. Alpha Centauri A was christened Regal Centaurus, which to Arab astronomers means the foot of the centaur. As you can see, this star, the brightest in the Centaur constellation, marks the location of one leg of this mythological creature, half horse, half man. Its companion, Alpha Centauri B, was named Ptoleman, which translates as ostriches. The origin of this choice of name remains a mystery. Finally, Alpha Centauri C, the third star to be discovered, owes its common name Proxima Centauri to its proximity to our solar system, literally meaning the nearest centaur star in Latin. Let's take a look at how these three stars are organized. The initial duo is made up of two main sequence stars, one a G-type star like our Sun, of almost identical age, and the other a K-type star. This means that Alpha Centauri A bears a striking resemblance to our Sun, also categorized as G2 V-type. But, unlike our Sun, this star has around 10% more mass and a 22% larger radius. Its luminosity is also estimated to be almost 50% greater. The secondary star is of spectral type K1V, hence its slightly orange luminosity. Slightly smaller and cooler than its counterpart, Alpha Centauri B has a mass around 90% that of the Sun and a diameter around 14% smaller. Its luminosity, also lower, is estimated at 0.445 times that of the Sun, with an apparent magnitude of plus 1.35. Both stars have an orbital period, slightly eccentric, that spans almost 80 years. When the two stars are at their closest, 11.2 astronomical units separate them before they continue their course, moving a maximum of 35.6 astronomical units apart. To give you an idea of their maximum distance at aphelion, this is equivalent to the distance between the Sun and Pluto. But if you'd like to have the privilege of observing these two stars as they come closer together, see you in May 2035. As far as Proxima Centauri is concerned, it took a long time for it to be confirmed as part of the original system, and with good reason. This faintly luminous star follows a much more distant orbit than the sparkling duo, the period of its orbit having been estimated at around 600,000 years. Its trajectory takes it 10,000 times further away from its companion stars than the distance separating our Earth from the Sun. This is why it took scientists long periods of observation before concluding that this red dwarf is indeed gravitationally linked to the Sun. Astronomers believe that the red dwarf was caught up in the luminous duo as it passed by. Moreover, the proper motion of Alpha Centauri AB's center of mass is estimated to have a radial velocity of 22.4 kilometers per second, or 14 miles per second, in the direction of our Sun. This double system, dragging Proxima along with it, is therefore insidiously approaching us, and will occupy various positions in our night sky as it slowly advances. Brighter and brighter it will reach the Hydra constellation in 27,700 years' time, coming ever closer to our Sun at around 3 light-years. Its apparent magnitude should then reach its peak, rivaling that of Canopus, the second brightest star after Sirius. Because of its relative proximity to our solar system, Alpha Centauri is a fascinating object of study for scientists. In fact, it is the site of numerous discoveries, each more exciting than the last, including the detection of candidate or confirmed planets in the vicinity of these stars. The system's main duo, Alpha Centauri A and B, could well harbor this type of object, but no confirmation has yet been provided. This hypothesis is all the more plausible given that no brown dwarfs or gas giants have been detected in the vicinity of this stellar pair, reinforcing the idea that a rocky planet could have formed there, at least in theory. According to astrophysicists, there could be a 75% chance that a telluric planet, and a potentially habitable one at that, could exist in such a system. In 2021, a planet orbiting Alpha Centauri A was suspected. This exoplanet candidate 1, estimated to be between the size of Neptune and half a Saturn, has an orbit approximately 1.1 astronomical units from the star, which it would cover in 1 year. As yet, this exoplanet has not been confirmed. Although the idea that it could be a background star has been dismissed, it could just as well be a dust disk, or even an artifact. Alpha Centauri B is no match for its close neighbor. It too seems to be accompanied by a planetary object. In October 2012, the sighting of a planet was announced by a Swiss astronomer. Named Alpha Centauri BB, this object, probably a telluric planet the same size as our Earth, is said to be experiencing terrible conditions. With an orbit very close to its star, and a period of revolution of just 3.2 days, one of its faces must be locked and constantly exposed to the 1,000 degrees Celsius or 1,800 degrees Fahrenheit of its sun. Since this statement, numerous studies have disputed the existence of this potential planet, including computer simulations. Although the actual existence of this candidate planet is in question, this challenge does not amount to a certainty either. In March 2015, another candidate planet was announced orbiting Alpha Centauri B, this time by a French astrophysicist. Slightly smaller in size than our Earth, this planet would also be too close to its star, although its orbit would last less than 20 days, and therefore be slightly wider. If the existence of this planet, named Alpha Centauri BC, were to be confirmed, it would unfortunately be unable to contain liquid water on its surface. Finally, it was with Proxima, the distant companion system, that not one, but 3 planets were detected for the first time. In August 2016, a team from the European Southern Observatory made this incredible announcement. Proxima Centauri B is the first confirmed exoplanet in this vast system. Probably telluric, this exoplanet has a mass at least equivalent to 1.3 Earth masses, and its radius could be 10% greater. What's more, its orbit, which it completes in 11.18 days, places it in the habitable zone of its host star, the system's sole red dwarf. Interesting, isn't it? 3 years later, in 2019, a second planet was detected in Proxima's vicinity. Potentially a cold super-Earth or mini-Neptune, this exoplanet, named Proxima Centauri C, has a minimum mass of around 5.8 times that of Earth. It has an orbital period of just over 5 years, a long period that is of course attributed to its distance from its star, which is around 1.5 astronomical units. Although its existence was initially questioned, it was confirmed in 2020 by Hubble telescope recovery images dating back to 1995. Finally, an official announcement in February 2022 confirmed the existence of a third planet orbiting Proxima. This is Proxima Centauri D, a surprising exoplanet with one of the lightest masses for this type of object, only a quarter the mass of our Earth. Located just over 4 million kilometers or 2.5 million miles from its star, this exoplanet takes just 5 days to complete a full orbit. Although located in the hot zone, it is unfortunately not in its habitable zone. However, if its average temperature is estimated at 87 degrees Celsius or 190 degrees Fahrenheit, it could well be that these polar zones present more moderate, even welcoming temperatures. In short, this exoplanet could be home to large expanses of liquid water. In other words, oceans. Not all the observations made within this star system concern planetary-type objects. In 2017, a study carried out using the vast array of antennas at the Chile-based ALMA Observatory revealed that radiation from coal dust had been detected all around the Proxima star. According to the Spanish team, led by Guillem and Glada, the Proxima star is surrounded by cosmic dust rings. Composed essentially of particles of rock and ice that have not yet agglomerated to form a planetary object, these are not unlike the asteroid belts in our own system. Located beyond the orbit of the Proxima B planet, 2 dust-laden belts seem to encircle the star and its planet. The first appears to be 1 to 4 astronomical units away from the star, while the second, much less luminous, is around 30 astronomical units away. According to scientists, the inner ring has a temperature of -233 degrees Celsius or 450 degrees Fahrenheit, and a mass of 0.01 Earth masses. What's more, this ring proved to be a formidable marker for providing a potential indication of the detected exoplanet's inclination. Indeed, when this observation was made, only the exoplanet Proxima Centauri B had been detected. This prompted astronomers to take an even closer look at Proxima's surroundings, which were clearly home to more than just a single planet. In comparison, this belt would have properties equivalent to those of our Kuiper belt. According to these latest observations, Proxima is most likely surrounded by a complex planetary system, bearing a striking resemblance to our own solar system. This suggests that Proxima and its planet followed a similar process. The hypothesis that Proxima B has been captured no longer holds water. This exoplanet was indeed formed in this atypical system. Moreover, the discovery of 2 other planets in the following years has since supported this idea. However, the existence of these rings was soon called into question. The following year, a study echoing the findings of the Spanish team examined the 10 hours of observations already made on March 24, 2017. But this new study, unlike the first, was not based on the average brightness of the star during its observation period. And this second approach has radically changed the previous conclusion. It turns out that in reality, Proxima's luminosity increased by a factor of 1,000 in less than 10 seconds, before returning to its initial appearance in just under a minute. In other words, Proxima suffered an extremely powerful, particularly brief and confusing event. The reflection of red light on particles, simulating rings, was nothing more than an excess of luminosity due to a stellar eruption. Nevertheless, the phenomenon is not at all exceptional and is reminiscent of the well-known behavior of red dwarfs, renowned for their somewhat explosive temperament. Proxima Centauri is no exception to the rule, which for those looking for habitable planets precisely in this zone does not bode well. Let's get closer to these unexplored worlds and take a closer look. Let's start by getting to know Proxima C, better known as Gliese 551c. This is the most distant of the 3 planets detected near the Proxima star. Its detection was announced in April 2019 by an Italian team of astrophysicists led by Mario Damaso. It was while studying the radial velocity data of the Proxima star using the HARPS high-precision spectrograph at the Chile-based European Southern Observatory that they noticed movements. Although insignificant, these can only be explained by the presence of a significant object, namely a planet. But to confirm the existence of such an object, further studies were required. Scientists took a closer look at recovery images from the Hubble telescope, which dated back to 1995. But instead of focusing, as in the 1990s, on potential planets with orbital periods of no more than 1,000 Earth days, they widened their search perimeter. After reanalyzing a wealth of astronomical data collected by Hubble, the researchers confirmed that there were indeed signs of an exoplanet in the vicinity of Proxima. As a result, the existence of Proxima C was confirmed in 2020, as it has a long orbital period. Images of Proxima C were even unveiled to the general public, thanks to the Sphere instrument on the European Southern Observatory's Very Large Telescope. Proxima C is therefore the first exoplanet, and the closest to our Earth, to have been immortalized by a lens. Together, these 3 studies have provided a wealth of information about this exoplanet. We now know that its mass is 7 times that of Earth, placing it in the category of super-Earths and mini-Neptunes. It takes more than 5 years to complete a full orbit, lasting exactly 1,928 days. This duration is of course related to its distance from the star Proxima, of which it is about 1.5 astronomical units away, i.e., almost 220 million kilometers, or 135 million miles. Given this configuration, could Proxima C harbor any form of life? This is highly unlikely, as life evolves well beyond the snow line, with the star's habitability zone lying between 0.05 and 0.1 astronomical units. With its equilibrium temperature estimated at just 39 kelvins, or around -234 degrees Celsius, it's likely that water can only exist there in its frozen form. Indeed, if Proxima C isn't a Lilliputian version of the famous gas giant Neptune, and indeed turns out to be a super-Earth, it may be covered by a thick mantle of ice. Let's continue our journey towards the star Proxima. The second planet we come across is Proxima B, also known as Gliese 551b. As mentioned earlier, this is the very first exoplanet discovered orbiting the star Proxima. As you can see, in terms of size, it's much larger, probably twice the size of its neighbor. Closer to its host star, at just over 7 million kilometers or 4 million miles, it orbits in 11.2 Earth days, receiving around 79% of the heat our Earth receives from the Sun. If it weren't for its sandy hues, it could almost be mistaken for our beautiful blue planet, couldn't it? Indeed, Proxima B is quite similar to our Earth in terms of mass, estimated to be at least 1.27 times that of Earth. Likewise, its radius appears slightly larger. But above all, because of its position, this exoplanet evolves in the habitable zone of the red dwarf, which grants it mild temperatures, particularly suited to the presence of liquid water on its surface. While the distance separating it from its host star gives it a temperate climate, let's not forget that the latter is a red dwarf, a star much colder than our Sun and up to 1,000 times less luminous. Proxima B is therefore much closer to its life vector than we are to the Sun, the distance being less than that separating the latter from Mercury. And this is not without consequences. Proxima B is strongly subject to the tidal forces of its parent star, which unfortunately synchronizes its period of rotation around its own axis with that of its orbit around the star. In other words, this exoplanet is tidally locked, probably exposing the same face to its host star at all times. But once again, this is only a hypothesis. Indeed, depending on the resonance with which it interacts with its local sun, the consequences might not be so catastrophic. In the case of a one-to-one resonance, the most pessimistic hypothesis, one of its faces would be eternally exposed to the star, with temperatures never falling below 40 degrees Celsius or 104 degrees Fahrenheit. The other side, meanwhile, would be plunged into endless icy darkness. On the other hand, if it were a 3-to-2 resonance, Proxima B could prove much more hospitable, although conditions would be far from those we enjoy on Earth. This means that the planet would be able to make 3 rotations on its own axis over a period of 2 years. Taking into account its orbit, which lasts 11.2 Earth days, this means that a day on Proxima B would stretch over 7.5 of our days, with relatively significant temperature variations. While this hypothesis remains conceivable, the presence of an atmosphere and a hydrosphere, both indispensable to the existence of any form of life, may generate other problems. Sometimes cold, sometimes hot, these elements generate irregular heating and thus convective movements, manifested by winds and ocean currents. Various models suggest that if Proxima B is covered by a gigantic ocean, the heat from the sunlit hemisphere could spread widely over the cold hemisphere along the equator. Different simulations based on more or less massive atmospheres put forward other ideas. In the case of a relatively thin atmosphere, heat distribution could be very uneven across the planet's surface. Conversely, a much more massive atmosphere, allowing maximum concentration of water vapor, could lead to more even heating, which would have an unexpected consequence. Proxima B would be largely ice-free, offering much more hospitable temperatures for the development of life. Now let's discover the third planet in this system. This is Proxima D, also called Gliese 551d by scientists. It lies just 4 million kilometers or 2.5 million miles from its host star, and is therefore located in the hot zone, slightly below the limit of the habitable region. What makes it special? It is one of the lightest exoplanets ever detected using the radial velocity technique, with an estimated mass 1/4 that of our Earth. Its discovery, albeit recent, has proved to be a technical feat. With such a tiny mass, the gravitational effect it produces on its host star is extremely weak. As a reminder, the radial velocity technique involves measuring the tiny movements of a star caused by the gravitational attraction of an orbiting planet. In this case, it enabled us to observe with incredible precision oscillations of Proxima Centauri measured back and forth at just 1.4 kilometers per hour or 1 mile per hour. It's easy to see why this type of object is so difficult to detect. Lasting 5 days, these small variations indicated the time needed for the planet to make a complete orbit around its star. It took the scientists almost 100 nights of observation to reach this conclusion, as the signal emitted by the star was particularly weak. But their patience was rewarded, as this discovery paved the way for many others. Because of its location in the system, Proxima D is probably a rocky planet. Its singularly low mass certainly prevents it from trapping gas in the same way as gas giants such as Jupiter, Saturn, or Neptune. It undeniably resembles a devastated Earth. Scorched in places by a constant average surface temperature reaching 87 degrees Celsius or 189 degrees Fahrenheit, while the polar regions experience more moderate circumstances. If this planet isn't the most hospitable, its discovery is nonetheless of the utmost importance. It suggests that all stars have their own multiplanetary systems. Thanks to the espresso spectrograph, it's a safe bet that many other planets previously invisible to the instruments will finally be unearthed. Another high-precision instrument will soon be pointed in the direction of Proxima C. Called Ristretto, it should enable us to observe Proxima's light reflected by the exoplanet. When this new instrument is in action, it will enable scientists to deepen their observations, and why not detect a hypothetical atmosphere or the possible presence of water? If the existence of these elements were to be confirmed on one of these planets, and on Proxima B in particular, it would be fantastic news. Proxima, as the closest star to us, is therefore an ideal target for scientists hoping one day to find any trace of life beyond our solar system. This is especially true now that Proxima B has been detected and located within the habitable zone of this red dwarf. However, there is much debate among scientists about the prospects of life near this category of stars, namely cool, low-mass M-type stars. These are among the most widespread in our galaxy, with a high frequency of exoplanets roughly comparable to Earth, and with equilibrium temperatures suitable for the presence of liquid water on their surfaces. However, red dwarfs are renowned for their unpredictable behavior, which has a particularly strong impact on their immediate environment. Indeed, these stars, although small, are active and unstable, with the usual stellar eruptions. As you may have guessed, Proxima is no exception to this rule. As part of a study of Proxima, covering some 40 hours of observation between April and July 2019, a team of researchers from the University of Colorado recorded a most spectacular stellar flare. It was recorded on the 1st of May, 2019, by 5 of the 9 instruments pointed in its direction, including the Hubble Space Telescope, the TESS satellite, and the high-performance ALMA terrestrial radio telescope, which alone brought together more than 60 dishes. According to the study, the star became 14,000 times brighter in ultraviolet wavelengths in the space of a few seconds. Scientists were amazed by the exceptional power of this burst of radiation. To give you an idea of the scale of the phenomenon observed, it turned out to be almost 100 times more powerful than the strongest flares ever seen on our sun's surface. Although it didn't produce much visible light, this explosion was unusually intense in terms of ultraviolet and radio radiation. Lasting just 7 seconds, it therefore produced millimeter wave signals. For scientists, this was a momentous observation. It confirmed that stars are capable of blazing in the millimeter range. This new type of signal is a godsend for researchers trying to learn more about how stars produce their flares. All the more so, as during the hours Proxima was under observation, astrophysicists noted a multitude of other flares on the star's surface. Not only does this mean that this type of flare cannot be described as rare, but more importantly, that such events are probably a daily occurrence. In fact, another team of astronomers had already announced in 2017 that they had captured a stellar eruption on Proxima's surface. Phenomenally powerful, it is likely to have been capable of destroying any Earth-like life present in a certain area. For the planets orbiting Proxima, this finding is far from optimistic about the presence of any form of life, at least as we know it. For if there were life on Proxima Centauri's nearest planet, Proxima B, it would have to be very different from anything on Earth. If not, any living organism that has experienced this stellar eruption has inevitably had a rough time of it. Planets in the vicinity of this star, which experience this kind of cataclysm on an almost daily basis, may see their potential atmosphere dwindle over time, if they even have one at all. Stripped of this protective bubble, these exoplanets would no longer be capable of harboring any kind of life at all, as they would be fatally exposed to deadly solar storms. But once again, this is nothing more than speculation. The high-energy radiation produced by this red dwarf has yet to concretely reveal its impact on the immediate environment. Further observations will be needed to shed light on an exciting subject: planetary habitability alongside the Proxima star. Apart from the problems caused by these stellar eruptions, there's another parameter, and not the least important one, to consider for researchers of potentially habitable planets. This is the star's lifespan. Assuming our humanity lasts several million or billion years, it would be a shame to have chosen as our promised land a planet evolving around the corpse of a star, wouldn't it? By the time our sun, in 1 billion years' time, begins its long transformation into a red giant, then undergoes a collapse followed by slow cooling, what will become of Proxima Centauri? A red dwarf is not to be confused with a low-mass star at the end of its life, having once shone brightly before slowly fading away. The latter has not undergone the same evolutionary process. A yellow dwarf at the end of its life generates helium fusion, gradually transforming into a red giant. Then, when this fuel is exhausted, it becomes an insignificant white dwarf, losing more and more of its luminosity until it glows red, before dying out forever and turning into a hypothetical black dwarf. While yellow dwarfs like our Sun have an estimated lifespan of 10 billion years, Proxima has a different destiny. Initially too small and hot to become luminous like yellow dwarfs, this star consumes its hydrogen extremely slowly. It belongs to the type of star with a convective interior. This means that energy flows from the core to the outer layers through the motions of the glowing plasma, Yellow stars, on the other hand, have a radiative interior, conducting their energy outwards from the core using a form of electromagnetic waves, thus rapidly stripping it of its fuel. Proxima, like all red dwarfs, has a particularly long lifespan, estimated at between a few tens and 1,000 billion years, or even more. By the time this red dwarf has exhausted all its resources and become a white dwarf in its turn, without passing through the red giant stage, it should gain considerably in luminosity. But before it reaches this stage, heating up its planetary system, a few billion years will have passed. Now you understand why this modest star is the focus of so much scientific attention. If other planets were to be discovered in its habitable zone, which is not excluded, the chances of conquering a new world would be greatly multiplied. As astrophysicists search for potential habitable extrasolar planets, they are equally on the lookout for hypothetical traces of extraterrestrial life. The SETI program for the search for extraterrestrial intelligence, created in the 1960s, is proof of this. On August 15, 1977, this collaborative program caused quite a stir. Jerry Emin, an astrophysicist from the state of Ohio, recorded a particularly strong signal with the Big Ear radio telescope, seemingly coming from a group of stars in the Sagittarius constellation. The signal astonished him so much that after printing the trace of this radio frequency, he circled it with a red line, then froze his amazement in the margin with an annotation, "Wow." This mysterious 72-second signal, emitted on the 1.42 GHz frequency, then became the famous signal "Wow." This strange message from the cosmos received by the Earth. However, listening to this radio wave was no accident. Indeed, before scientists set out to listen to the sky in the hope of detecting potential ET signals, they calibrated their equipment. To give themselves every chance of one day listening for such a signal, their radio telescope was set to a precise wavelength, known as the 21-centimeter array. This choice was based on an obvious deduction. The electromagnetic radiation produced at this wavelength corresponds to that which best penetrates hydrogen. Hydrogen is the most abundant element in the cosmos. The recording of this signal came as a great and unexpected surprise, generating doubt. A more down-to-earth explanation was sought. Due to an international agreement, the frequency used is reserved exclusively for this program, precisely to avoid any terrestrial interference. What's more, no known natural phenomenon can emit such a signal. The hypothesis that a pulsar is at the origin of this signal has also been studied, with no concordant results. Even the possibility of a computer error in the system was considered, but dismissed for lack of evidence or recurrence. Finally, the passage of two comets through the radio telescope's listening field has been the subject of debate ever since, their existence having only been proven much later, in 2006 and 2008. For many scientists, however, the latter explanation does not seem credible at all, as various pieces of evidence support it. Since then, a complementary project, Breakthrough Listen, was launched in 2015. Its aim is to focus on unexplored radio frequencies identical to those commonly used on Earth for all kinds of communications. In April and May 2019, radio signals were intercepted from the vicinity of the Proxima Centauri star. The source of these signals has been named BLC-1 for Breakthrough Listen Candidate 1. While astronomers on this project regularly spot unusual radio wave bursts, these are usually explained by human interference. But this latest one, detected 5 times during some 30 hours of observation, has passed various tests, greatly arousing their curiosity. All the more so as it occupies a particularly narrow band of the radio spectrum, the only source known to date capable of transmitting at 982 MHz being human. For scientists, the task now is to sort things out. Is it really an extraterrestrial technosignature, as many exobiologists and science fiction novelists dream? Or is it yet another case of interference from Earth? But researchers aren't content to just listen to the universe. Over the past few decades, several messages have been sent to specific regions of space, addressed to a potential extraterrestrial civilization. While most messages have been transmitted by radio, some in the form of images encrypted in binary code, others have been composed of drawings, like the one attached to the Pioneer 10 probe. An even more sophisticated message, 2 golden disks containing images of the Earth, musical data or ambient sounds of our planet traveled through space on the Voyager 1 and 2 probes. These messages, like bottles thrown into the sea, should they one day encounter a form of life, are nevertheless no guarantee of a future dialogue between civilizations. Who is to say that a potential life form beyond our planet would be able to intercept these messages? After all, these supposed extraterrestrials may not perceive their environment as we do. Their language could have evolved in a telepathic mode, rendering sight and hearing obsolete. Nevertheless, as long as the contrary has not been formally demonstrated, the hope of finding a trace of life in the Alpha Proxima system, or at the very least a habitable planet, why not one that can be terraformed, is still alive and well. For the record, let's not forget that our own system could yet reveal some of its secrets. Astrophysicists suggest that a 9th planet, as yet unobserved, may exist in the outer reaches of our solar system, somewhere in the Kuiper Belt. If the existence of this celestial body were to be confirmed, which could well happen in the very near future, it could explain the unusual motions observed with certain objects evolving beyond Pluto's orbit. So, with our eyes riveted on the promising Alpha Centauri system in search of exoplanets, even if it is a fantasy, the idea is not absurd. Especially as techniques for detecting distant objects, even those of low mass, are becoming increasingly precise. But while we await major revelations, such as, why not, the discovery of an exoplanet similar in every way to our Earth, let's take a look at what life might look like on the planets we've observed. As we've seen, Proxima D is far too close to its host star to offer us a comfortable place in the Sun. Its telluric appearance hides an inferno of fire and ice, as the planet is trapped in a synchronous rotation. On the one hand, its sky is eternally ablaze with the glow of the red dwarf it borders, its atmosphere a toxic mixture of gases. Violent, fiery winds plow its rocky surface, resembling a desert of molten glass. Its night side, also desolate, is an ice abyss, plunged forever into cosmic darkness. Even if any trace of life could ever have formed on this planet, even if only in the form of bacteria, at present, it can only be completely annihilated, at least on its day side. As for Proxima C, the most distant of the 3 planets orbiting Proxima, the picture is not much brighter. Its status is still unclear. Is it a gas giant resembling a mini Neptune, or a super-Earth? In either case, it's an extremely cold world, far too far from the habitable zone of its host star. However, if it turns out to be a super-Earth, the idea that it could harbor life in a form other than the one we know may not be so far-fetched. Imagine that this planet contains large quantities of water. In that case, it could be entirely covered by oceans that are completely frozen, or at least several kilometers or miles deep. Unwelcoming, isn't it? Now imagine what its seabed might look like. Although completely deprived of the weak glow emitted by the local sun, they could nevertheless experience temperatures more favorable to the development of a certain biosphere. The regular activity of submarine volcanoes could enable this singular environment to keep simple multicellular organisms alive in such ocean depths. Of course, this is all speculation, not to say daydreaming. Let's now turn our attention to the most attractive of these 3 planets, Proxima B, which has enthusiasts enthralled. While it does indeed lie in the temperate zone surrounding the red dwarf, its proximity makes it particularly vulnerable. As it too is locked in by tidal forces, this planet probably consists of 2 distinct worlds, a day side and a night side. In theory, its overall temperature allows for the presence of liquid water on its surface, the supreme condition for all life. But does it still have an atmosphere, which is also essential? If so, it would be plausible for temperatures to be in the region of -30 degrees Celsius or -22 degrees Fahrenheit on the shady side, and 30 degrees Celsius or 86 degrees Fahrenheit on the light side. Unfortunately, if an atmosphere is or was present on the surface of Proxima B, some scientists agree that its existence is highly compromised. Remember the activity described earlier of Proxima Centauri, its recurring tantrums concretized by intense ionizing rays and repeated solar storms. Because of its short distance from its red dwarf, this planet is particularly exposed to its X-rays and ultraviolet rays. According to researchers, the latter could be up to 100 times more powerful than those we receive from the Sun. Despite this, the idea that Proxima B still has an atmosphere has not been completely ruled out. Numerous simulations of planetary worlds evolving in systems similar to Proxima Centauri show that the majority of planets are either completely covered by a vast, thick, icy ocean or have become barren rocks. Far rarer planetary objects comparable to our Earth, however, exist in orbit around old red dwarfs that have become less active. In the case of Proxima B, this relatively massive super-Earth appears to have absorbed large quantities of water particles and surrounding gas in its early stages. If this hypothesis is confirmed, a particularly dense atmosphere of oxygen and nitrogen could envelop it, masking a mysterious oceanic world. The existence of this atmosphere, potentially 10 times more abundant than that which protects our Earth and of oceans several kilometers deep, cannot be ruled out. Despite the explosive nature of its neighboring star, Proxima B has not yet been completely stripped. Some scientists even consider that it may have retained a sufficient atmosphere and a sizable hydrosphere. The planet's large size is therefore a definitive advantage, especially since the presence of a magnetic field is highly probable. A planet of this size, though tidally locked to its star, may not yet have come to a complete stop in its rotation. Its core could still be hot and mobile for a long time, generating a substantial magnetic field, perhaps even greater than that of our Earth. Now imagine that these three factors were combined: a dense atmosphere, a considerable hydrosphere, and a strong magnetic field. They would provide the conditions necessary for the survival of many forms of life, protecting them to a large extent from the harmful and devastating radiation of the Proxima star. Although this world, if it really exists, is plausibly an essentially aquatic one, failing to be truly hospitable, it remains no less captivating. In a recent study of 17 exoplanets, NASA's Dr. Lene Quick and her colleagues shed some light on their habitability. According to their findings, Proxima B, like the other extraterrestrial worlds studied, may unfortunately not be as hospitable as hoped. On the one hand, it seems less dense than our Earth, suggesting that it would be composed essentially of ice and water rather than rock. The surface temperature, a priori colder than first estimated, implies that this oceanic planet would be completely covered by a mantle of ice. The thickness of this mantle is estimated at nearly 58 meters or 190 feet. On the other hand, based on the intensity of geysers on Europa, one of Jupiter's moons, they calculated that Proxima B could have an extremely high rate of geyser activity. This appears to be hundreds or even thousands of times greater. Cryovolcanic eruptions in the deep ocean would expel considerable plumes of steam and ice particles far from the surface. Proxima B would in fact be dotted with abundant geysers cutting through its ice mantle, especially as the latter appears to be much thinner than on many similar objects. All these assumptions are based on observations made using the latest technology and on scientists' current knowledge. In the near future, as science continues to advance, these assumptions may be called into question. As you may have noticed, what seems to be true one day may turn out to be false the next. So who knows? Perhaps a future study will bring other conclusions, perhaps more favorable to a long-awaited discovery. With this in mind, scientists have long been considering sending out scouts in the form of onboard technologies. But what are their practicalities? Assuming that our current technology would allow such an expedition, how long would it take a spacecraft today to reach Proxima, the star that is our solar system's closest neighbor? Unfortunately, far too long. Currently, the fastest space probe ever designed is NASA's Parker Solar Probe. Launched in August 2018 to study the outer atmospheric layers of our Sun, it has been setting record after record ever since. Its latest came on September 27, 2023, when it reached a record speed of 635,000 kilometers per hour, or 395,000 miles per hour. This is 15 times faster than the fastest manned spacecraft. If we could travel at the same speed, it would still take us almost 7,300 years to reach Proxima Centauri. Assuming we could travel at the speed of light, this journey would be reduced to 4.2 years. To date, only 2 probes have crossed the boundary of our solar system. Launched on September 5, 1977, the Voyager 1 and 2 probes are the first man-made objects to travel through interstellar space. Voyager 1 was the first to cross this boundary in 2012. 35 years after its launch. It has enabled scientists to learn more about our Sun, its interactions with particles and magnetic fields outside our heliosphere. These observations have provided key information for future missions. As for the Pioneer 10 and 11 probes and the New Horizons probe, launched respectively in 1972 and 2006, while they have reached the limits of our solar system, the former are no longer in a position to emit anything. New Horizons, whose primary mission was to fly over the planetary objects of our solar system, will never be able to catch up with the Voyager probes. As you can see, space travel to the Proxima star is still a fiction. NASA's ambition was to develop a technology that would enable a probe to travel at a considerable speed, around 10% of the speed of light, in order to complete the long journey in just 44 years. At least that's what the team at NASA's Jet Propulsion Laboratory was aiming for in 2016, with the goal of sending a probe to explore Proxima B by 2069. To give you a benchmark, it would take Voyager 1 around 80,000 years, assuming it ran into no obstacles, to get close to Proxima Centauri, its cruising speed being 16 kilometers per second or 10 miles per second. NASA is therefore looking into ways of reaching Proxima in the shortest possible time, especially since if this feat were to be achieved, it would still be more than 4 years before any recorded data would reach us on Earth. A major technological breakthrough is therefore essential if a mission of this scale is to succeed. A combustion engine powered by a nuclear fission reaction could achieve this. Unfortunately, according to scientific estimates, it would take 1,000 years. Engineering using pulsed nuclear propulsion, still theoretical, would enable this crossing to be made in a century, but without guaranteeing the safest possible journey, as its nuclear payload represents a considerable risk. According to astrophysicist Michael Gillon, nuclear fusion, provided that a nuclear fusion engine is mastered, which is still a long way off, would shorten the journey time to just 36 years. Faced with this more than ambitious project, NASA has finally associated its Innovative Advanced Concepts Program, or NIAC, with a private initiative called Breakthrough Starshot. Launched in 2016, Breakthrough Starshot is a commercial research and engineering project estimated to cost $100 million. Many visionaries who also dream of conquering space have taken part in this project, which aims to explore deep space and potentially discover other habitable planets. Their primary objective is to encourage technological innovation by bringing together eminent scientists to make a voyage to Proxima Centauri possible in a few decades' time. Research teams are hard at work on advanced technologies that will ultimately benefit humanity. These should revolutionize our understanding of the universe and offer future generations the opportunity to finally explore other interstellar worlds aboard spaceships. One of the main challenges facing researchers is to develop a propulsion system capable of propelling a spacecraft at a speed equivalent to 20% of the speed of light. To achieve this ambitious goal, researchers are currently developing 3 key programs. The first is the design of a miniaturized spacecraft known as starships. These nanoprobes, equipped with computer chips and a whole range of communication systems, must withstand the extreme conditions they will be confronted with. The second is the development of a propulsion system based on lightweight sails, the light sail system. Based on optical technology, these sails are made of a material only a few hundred atoms thick. Last but not least, the development of a ground infrastructure to supply, via a laser system, the energy required by this light sail to propel and steer the starships towards its destination, Alpha Centauri, and more specifically, the star Proxima and its planetary system. To multiply the chances of succeeding in this crazy gamble, 1,000 star-chipped ships, each weighing no more than a gram. Thanks to the laser's unrivaled power of 100 gigawatts, these nanovessels would then be able to reach a speed of around 20% of that of light. Like a swarm, these extraordinarily autonomous probes will progress with perfect synchronization to form a mesh network covering an area of around 100,000 kilometers or 62,000 miles in diameter. This process should ensure that a minimum number of probes, despite a high loss rate or poorly controlled direction, reach the coveted target of Proxima. The scientists' efforts have just been rewarded, with NASA selecting their concept for Phase 1 development under their NIAC, or Innovative Advanced Concepts program, at the start of 2024. The only solution at present, therefore, is to reverse the rocket. Instead of the rocket expelling a material to be used as fuel, it is necessary to launch something onto the vessel that will enable it to move forward. In this case, like the wind blowing over the sail of a boat, photons would strike the photovoil of each of these nanoprobes. Although scientists have made tremendous strides, such a mission is unlikely to see the light of day before 2075. The concept, though very promising, must overcome enormous difficulties. These include the robustness of the sail. Will it be able to withstand the heat generated by the laser beam? Or to sudden accelerations? Or the gas and dust it might encounter? On the other hand, control from Earth will be impossible. Scientists therefore have to develop genuine robotic probes. The swarm, as they are called, must be perfectly autonomous. Finally, the manufacture of this high-tech swarm and the construction of a terrestrial laser system, not to mention the research work, represent a staggering budgetary outlay. Even if each of these probes on a gram scale does not generate exorbitant manufacturing costs, the project as a whole is the most ambitious ever envisaged. In the silent immensity of space, the Alpha Centauri system shines like a distant promise, and like a lighthouse attracts our boldest dreams. Imagine a world where the stars are no longer out of reach, where the secrets of the universe are revealed to us on fabulous interstellar journeys. Proxima B, the exoplanet that's raising our wildest hopes, could hold the key to our deepest questions. Is it the cradle of extraterrestrial life? Do its oceans conceal strange forms of life? Is it a potential future home for mankind? Or, on the contrary, a place of nameless desolation, begging to be fled? The technological advances under development, these robotic probes that could one day split the vacuum of space, are not mere tools. They are messengers of our curiosity, probably the pioneers of a new era. Each of their discoveries, beyond helping us to take another step towards understanding our place in this great whole, will be a formidable legacy for our future generations. More than a scientific feat, the project to spin off Proxima using these solar minisons is a veritable symbol. Alpha Centauri and the Proxima system in particular, may still seem a long way off today, but every step we take brings us closer to the moment when we can say that we are travelers among the stars. And who knows, perhaps in just over a century's time, the first images of Proxima B will reach us. Let's continue our journey through space to reach the star Sirius, located 8.6 light-years from Earth in the constellation of the Great Dog. Sirius A, with its scientific name Alpha Canis Majoris, is the brightest star in our night sky and the 5th closest star to the solar system. You're probably wondering how you can see Sirius so well from Earth without even needing a telescope, while Proxima Centauri, the closest to us after the Sun, is not visible. This is simply because Sirius is a very massive star. It is 1.8 times larger than the Sun, and 2.3 times more massive. Its surface temperature is estimated at more than 9,600 degrees Celsius, or 17,300 degrees Fahrenheit. The star Sirius A has a much smaller companion star, Sirius B. This white dwarf star, which is about the size of the Earth, has a mass equivalent to the Sun. Sirius B was discovered in 1862, a discovery that marks the first in the history of astronomy. It is separated from Sirius A by a distance of about 20 astronomical units, or 20 times the distance between the Earth and the Sun, which is equivalent to the distance between the Sun and Uranus, for example. Its orbit is elliptical and lasts 50 years. The two Sirius stars are therefore more or less distant, depending on the year. In 2025, it will be the largest possible separation between the two stars. Moreover, Sirius A is moving away from us, albeit very slowly. In the 17th century, the astronomer Edmund Halley compared the position of Sirius in the night sky to the position recorded by the astronomer Hipparchus in the 2nd century BC. In 18 centuries, the star has moved about 30 arc-minutes, the size of the full moon. It may surprise you that the existence of Sirius was already known in the Hellenistic era. It is even the Greeks who gave it its name. Sirius comes from the Greek Syros, the fiery or burning one. If we look at the history of astronomy, it is not so surprising, because already the Babylonians observed the sky 3,000 years before our era. And Sirius A is so bright that you can't miss it. This star has fascinated people over the centuries. In ancient Egypt, it was associated with the goddess Isis, the wife of Osiris, and one of the 5 children of Nut in the sky, and Geb was the god of the earth. Moreover, the heliacal rising of Sirius, that is to say, the movement when it was the last star to shine before the sunrise, coincided with the summer solstice and the fertile floods of the Nile. It may also be interesting to know that the heliacal rise of Sirius has shifted in time. Indeed, the axis of rotation of the Earth describes a cone in space in 25,800 years. At this moment, the axis of rotation points to the North Star, which is used to indicate the North Pole. But it has not always been so. Over the centuries, this role has been assumed in turn by the star Kochab of the Little Dipper at the time of Homer, and by Thuban, or Alpha of the Dragon, at the time of the construction of the pyramids. In 10,000 years, it will be the star Vega in the constellation of Lyra that will show us north. Before we continue our journey, here are some tips for seeing the star Sirius the next time you look at the stars from Earth. The star Sirius is visible throughout the winter in the constellation of the Great Dog. It can be seen from anywhere on Earth. If you are in the northern hemisphere, the star is part of the winter hexagon. To help you find the brightest star, you can use the 3 stars in Orion's belt, also called the 3 Magi. They point in the direction of Sirius. Just draw a line from these 3 stars. Sirius should not be difficult to spot, since it is much brighter than the others. With a 400mm telescope at least, you can also see the white dwarf Sirius B. One last tip. Sirius is rather low in the sky. The light emitted by the star must therefore cross a great distance of atmosphere to reach us. The turbulence in the atmosphere can produce a flickering effect. That's why sometimes you can get the impression that Sirius is flickering a bit, like an airplane crossing the sky. We are now 35 light-years away from our solar system. The exoplanet in front of you must look familiar. That's normal. It's the closest exoplanet ever photographed in direct view. It is also one of the few exoplanets ever photographed. The picture you have probably already seen was published by a team of researchers from the University of Hawaii on July 6, 2021, in the journal, the Astrophysical Journal Letter. Coconuts 2b is a gas giant like Jupiter. It orbits a star named Coconuts 2a, or L3426. Coconuts 2a is a red dwarf with a mass equivalent to 1/3 of that of the Sun, with a fast rotation period of 2.83 days. The Coconuts 2a star system is quite young and is estimated to be between 150 and 800 million years old, as is the exoplanet Coconuts 2b. For comparison, our Sun is 4.6 billion. It was detected in 2011 by the WISE satellite and then studied through the Coconuts program, which analyzes the characteristics of celestial objects and distant star systems. In 2011, the data received by the WISE satellite suggested that Coconuts 2b was a celestial object drifting in space with no particular orbit. 10 years later, it was concluded that the exoplanet does orbit a star, with an orbital period of more than 1 million years, which is huge. This can be explained by the great distance between this planet and its star, 6,471 astronomical units, which is more than 6,000 times the distance between the Earth and the Sun. Moreover, Coconuts 2b being very far from its star, it is a gaseous planet with an average temperature of 161 degrees Celsius, or 320 degrees Fahrenheit. It makes one revolution around its star, in addition to the one around the Sun. Fortunately for us, this distance allowed us to obtain a direct image of it, without the planet being drowned by the light of its star. Another impressive fact: Coconuts 2b has a mass 6 times greater than that of Jupiter. To give you an idea, Jupiter is already 317 times the mass of the Earth. Coconuts 2b is qualified as an extreme star because of its colossal mass. The extreme stars are all the stars whose characteristics are so singular that they seem inconceivable. Coconuts 2b is thus the second largest exoplanet discovered to date. Let's continue our journey to K2-18, the star system that could host another Earth. We are now 63 light-years from Earth, in the constellation of Pisces. This is where we find the coldest star in the universe, WD 0806 661b. Stars are, by definition, hot bodies. They are made of hot gas, and like a constantly burning engine, they constantly consume energy by emitting heat. The star in front of you holds the record as the coldest star in the universe. It is a brown dwarf star with a surface temperature between 27 and 80 degrees Celsius, or between 80 degrees Fahrenheit and 180 degrees Fahrenheit, temperatures close to those of the Earth. As you can imagine, cold stars are not that common in the universe. The Sun is not the hottest star, and yet its temperature is 6,000 degrees Celsius, or 10,800 degrees Fahrenheit at its surface, and 15 million degrees Celsius, or 27 million degrees Fahrenheit, at its core. It must be said that brown dwarfs are hardly considered as stars. Their formation is similar to that of a star. That is why they are considered as stars. But they are at the limit between a small cold star and a large hot planet. WD 0806 661b is 6 to 9 times more massive than Jupiter. Categorized as an ultra-cold dwarf because its temperature is below 2,400 degrees Celsius, or 4,350 degrees Fahrenheit, WD 0806 661b, by its mass, is at the limit with the supergiant planets. By definition, a star must have a sufficient mass to trigger the nuclear fusion of hydrogen in its core. The fusion of hydrogen atoms in the core of a star releases a large amount of heat and light, powering the star like a huge engine throughout its life. The minimum mass for this process to occur is about 80 times the mass of Jupiter, or 10% of that of the Sun. Planets do not have a mass large enough to trigger this kind of reaction. But brown dwarfs are very large planets, between 10 and 80 times more massive than Jupiter. They are thus massive enough to allow the fusion of deuterium, also called heavy hydrogen, but not hydrogen. The structure of deuterium facilitates its fusion, despite the relatively low mass of brown dwarfs. Too big to be part of the category of planets, and too small to fit in that of stars, brown dwarfs form a separate category, hence the nickname of failed star. But if brown dwarfs are given a sad nickname, it should not be deduced that their knowledge is of no interest. NASA explains that brown dwarfs could occupy an important part of the mass in the universe. Given that they are not very luminous, it is perhaps towards them that we should turn to finally solve the thorny problem of the missing mass. A mass whose influence is suspected, but that we have not yet managed to detect. Let's continue our journey towards K2-18b. We are now 84 light-years away from Earth. Have you noticed this strange starless planet, which seems to float alone in the universe? It is the exoplanet PSO J318.522. In 2013, an international team of astronomers announced in the journal Astrophysical Journal Letters that they had discovered a lonely world through the Pan Stars 1 telescope installed near Haleakala in Hawaii, a gaseous exoplanet that orbits no star. Is this even possible? This announcement has shaken the scientific community because never before has an object floating freely in space been discovered. The mystery is even thicker as PSO J318.522 has all the characteristics of young planets orbiting other stars: mass, color, and energy. Astronomers have estimated that this strange planet belongs to a collection of stars the Beta Pictoris moving group, which formed about 12 million years ago. It is therefore very young on the scale of the universe. It is massive, since it is 6 times the mass of Jupiter. It is, however, the lowest mass ever observed for a free-floating body. PSO J318.522 was discovered in 2010, and it is in 2013 that its discovery was confirmed. Astronomers were then studying brown dwarfs, the objects of which we observed a specimen just before. The telescope had been set to detect the faint red glow of brown dwarfs, and it was an exoplanet with a very red spectrum that was discovered. By the way, the spectra of brown dwarfs and gas giants are similar, and the confusion is often made between these two celestial objects. The young planet, PSO J318.522, was observed by a direct observation method. Generally, planets found by direct detection are difficult to study because they are located next to much brighter stars. But since PSO J318.522 is not located near a star, its observation will be facilitated, which can give scientists a lot of information about the internal mechanisms of giant gas planets. Since that discovery, other solitary exoplanets have been found, including CFB-DSIR 2149-0403, which was discovered in 2012 by a team of researchers at the University of Montreal and described as a planetary mass-free object, or brown subdwarf. So how have astronomers explained these wandering planets since these discoveries in the early 2010s? One theory states that these planets would have been ejected from their home systems. There could be smaller planets nearby, such as Earth, that current technologies do not allow us to detect. Let's continue our journey in the universe with another strange exoplanet, TOI 1452b, a super-Earth-like exoplanet that is suspected to be an ocean planet. First of all, it is necessary to understand the term of super-Earth. It designates an exoplanet which has a mass between that of the Earth and that of a giant planet. The mass of a super-Earth is thus between 1 and 5 times the mass of the Earth and 10 times the mass of the Earth. Be careful, a super-Earth is not necessarily a planet that could harbor life. Only the mass is taken into account to qualify an exoplanet as a super-Earth, without taking into account the other conditions necessary to harbor life, such as the presence of water and the composition of the atmosphere, for example. TOI 1452b is a super-Earth located at 100 light-years from Earth in the Dragon constellation. It orbits in the habitable zone of a red dwarf located in a binary system. Its star is therefore smaller than the Sun, which is a yellow dwarf. Spotted by the NASA TESS telescope, TOI 1452b was then observed with powerful instruments. These observations showed that it could be an ocean planet, i.e. a planet covered with a vast and deep layer of water. TOI 1452b has been detected thanks to the transits method, which consists in measuring the light of a star in search of possible decreases of luminosity. A small decrease in brightness at regular intervals is a reliable indication of the presence of an exoplanet orbiting the star, because when the planet passes in front of its star, it occults the star, which causes this decrease in brightness. TOI 1452b passes in front of its star every 11 days. The data collected and analyzed showed that this planet is about 70% larger than the Earth, with a mass of 5 times that of our planet. The solar system of TOI 1452b is said to be binary because it has 2 stars separated by 97 astronomical units, or 2.5 times the distance between the Sun and Pluto. It is around the larger of the 2 stars of this binary system that the ocean planet orbits. An article published in the Astronomical Journal indicates that TOI 1452b is a rocky planet, but with a density less than that of the Earth. The Earth has very little water compared to its mass. Indeed, water represents less than 1% of its mass. Unlike other stars, such as the satellites of Jupiter, Ganymede, and Saturn, Titan and Enceladus, the liquid water on these moons represents from 16 to 46% of the total volume. There is more liquid water inside Europa, Ganymede, and Titan than on Earth. Astronomers are leaning towards the hypothesis that the relatively low density of TOI 1452b is linked to the presence of a lot of water, especially since this planet is neither too close nor too far from its star, which would allow the appearance of water in liquid form. According to estimates, water could constitute 30% of the mass of TOI 1452b, as on the moons Ganymede and Enceladus. There are other exoplanets that are called ocean worlds because of their density, but TOI 1452b is definitely the most interesting because it is relatively close to us. The James Webb Telescope, put into orbit in December 2021, should give even more information on this ocean planet, which is only 100 light-years away from Earth. We will then be able to confirm whether or not TOI 1452b is an ocean planet. It is time for us to leave behind this mysterious planet. We finally arrived in the star system K2-18. It's been a long journey, but you won't regret embarking on this journey in search of the most promising planet for an alien life form. We are 124 light-years from Earth in the constellation Leo. The K2-18 star system you are looking at is also known as EPIC 2019125552. This planetary system is organized around a red dwarf, and it has at least 2 planets, a hot super-Earth called K2-18c, and a smaller, Neptune-like planet called K2-18b. The central star of the K2-18 star system is a red dwarf. Smaller than the Sun, it is about 1/3 of its mass. Its luminosity is only 3% that of the Sun. The surface temperature of this red dwarf is 3,220 degrees Celsius, or 5,800 degrees Fahrenheit, half that of our Sun. It takes about 39 days to make a complete turn on itself, against 25 days for the Sun at the equator, and 36 days at the poles. The star K2-18 is located 124 light-years from Earth, which makes K2-18 a relatively close star system. You surely realized this when you came here. Between the Sun and the red dwarf K2-18, there are only about 15,000 stars. The star K2-18 is very different from the Sun, and not only for reasons of mass, temperature, or rotation on itself. It is a red dwarf, a completely different class of star than the Sun, which is a yellow dwarf. Before continuing to explore the K218 star system, let's start by examining this red dwarf. The first red dwarfs were discovered in the 20th century. Proxima Centauri, which we observed earlier, was discovered in 1915, followed by Barnard's star, almost 6 light-years away from our Sun. Red dwarfs are the smallest stars. Their mass is between 8 and 40% of that of the Sun. They are also the most frequent stars. More than 75% of the stars in the Milky Way are red dwarfs, 160 billion out of 300 billion. Moreover, among the 30 nearest stars, 20 are red dwarfs. It is believed that there are billions of super-terrestrial stars orbiting red dwarfs in the Milky Way alone. No red dwarf is visible to the naked eye from Earth, for the simple reason that they are not bright enough. Red dwarfs have, on average, a luminosity equivalent to 1% of that of the Sun. The largest of them can reach 3 to 4% of the Sun's luminosity, not more. Not very massive, red dwarfs are not very hot, and their temperature is always lower than 3,730 degrees Celsius, or 6,700 degrees Fahrenheit. According to astrophysicist models, and given their physical properties, red dwarfs would be likely to shine relatively constantly for hundreds of billions of years, several tens of times the age of the universe. All the red dwarfs that we observe today are only at the beginning of their existence. While some of them, like the red dwarf Proxima of the Centaurus, will shine for more than 1,000 billion years, our Sun will slowly die out in 8 billion years by transforming into a white dwarf. This is enough to make you dizzy. We must not confuse red dwarfs and white dwarfs, which are the corpses of small stars, whose light is extinguished after several billion years. To make it clearer, I will tell you about the Hertzsprung-Russell diagram, which was developed in the early 20th century. The Hertzsprung-Russell diagram classifies stars according to their absolute brightness. This luminosity depends on several factors: the mass of the star and the temperature at the surface. The more massive a star is, the stronger its brightness. Each star does not have a fixed place on this diagram. Remember that the universe and its objects are constantly evolving. The initial mass of the star determines its placement on the diagram, but also its evolution. There are several groups of stars: main sequence stars, white dwarfs, blue giants, red giants, and supergiants. Stars will move from one group to another during their evolution. Let's take the example of the Sun. The Sun is a yellow dwarf. It is currently located in what is called the main sequence of the diagram. The stars of the main sequence are those inside which hydrogen alone is consumed by nuclear reactions. The consumption of hydrogen produces helium, which in large quantities will hinder the nuclear reactions in the heart of the star. When the star has consumed 10 to 20% of its total hydrogen, it will begin to collapse. A nuclear fusion reaction occurs, and the star will swell while cooling. It is at this point, when the drop in temperature results in a red shift, that the Sun will become a red giant. Over billions of years, the star will gradually die out. When the Sun has reached a very low temperature and can only radiate the remaining heat, it will become a white dwarf, the ultimate stage of stellar evolution, before cooling completely, billions of years later, to become a black dwarf. As for red dwarfs, they have a longer lifespan than the Sun. They can consume a larger proportion of hydrogen because the conversion of hydrogen into helium is very slow. In addition, helium does not accumulate in the center of the star, but circulates inside. Red dwarfs will never become red giants because they heat up slowly until all the hydrogen is consumed. Since the Big Bang, there has not been enough time to observe the terminal sequence of a red dwarf, and yet about 13.8 billion years have passed. The K2-18 star system is home to at least 2 exoplanets, K2-18b and K2-18c, which orbit the star K2-18. Both are more massive than the Earth. They are rocky superterrestrials, with a mass of 7 and 8.6 times that of the Earth. The closest planet to the star K2-18 is K2-18c. This hot super-Earth was discovered in 2017 and confirmed in 2018. It was in fact by studying K2-18b, which had been discovered earlier in 2015, thanks to the American satellite Kepler, that the researchers spotted the signal of K2-18c and were able to discover this exoplanet. K2-18b is indeed the one that interests astronomers the most. It is the most distant from the star K2-18. It is between 6 and 10 masses of the Earth, and its radius is 2.3 times larger than that of our planet. It has an orbital period of 33 days and an equilibrium temperature of about minus 23 degrees Celsius, or minus 9.4 degrees Fahrenheit, which is very close to the Earth's equilibrium temperatures of minus 18 degrees Celsius, or minus 0.4 degrees Fahrenheit. As a reminder, the equilibrium temperature of a planet is the theoretical temperature of its surface in the absence of an atmosphere. Astronomers believe that K2-18b has all the characteristics to possess liquid water on its surface, which would make it habitable. Its density, however, seems far too low for it to be a rocky planet. Either K2-18b is a rocky planet with liquid water on its surface, or it is a planet covered by a thick layer of ice. In other words, it is a rocky super-Earth, surrounded by a small gaseous envelope, or a gaseous mini-Neptune, essentially composed of water and covered with ice. In any case, K2-18b is made up largely of so-called volatile constituents, which form a fluid envelope with elements like molecular hydrogen, helium, or water. As often in the observation of the universe, nothing is certain yet. These two hypotheses hold true, and only the observations of the James Webb Telescope can tell us more. Indeed, the telescope is capable of analyzing the atmosphere of exoplanets, as it proved with the exoplanet WASP-39b. I remind you that James Webb has demonstrated the presence of CO2 in the atmosphere of WASP-39b, a hot gaseous planet located 700 light-years away in the Virgo constellation. The principle is quite simple. When the exoplanet passes in front of its star, the light from the star will pass through its atmosphere. Scientists will then be able to study the spectrum of the light, in particular, the absorption lines, which are sort of holes caused by the gases that the light has passed through before reaching us. Each gas has its own absorption lines. Just by studying the spectrum of light from K2-18, passing through the atmosphere of K2-18b, astrophysicists will be able to determine which gases are present and in what proportions in the atmosphere of this exoplanet. In any case, the exoplanet K2-18b is considered by many astronomers as one of the most promising exoplanets for the existence of an extraterrestrial life form, although it is more than 1 billion million kilometers and a half away from Earth. Before diving into the heart of this planet, let's review the criteria that a planet must meet, according to scientists, to be likely to host life. For decades, scientists have limited themselves to our solar system. The search for life on Mars or Venus was the subject of many observations and space explorations. In the 1990s, the question of the existence of extraterrestrial life was revived with the discovery of exoplanets. Exoplanets are, I remind you, planets that orbit other stars than the Sun. They are, in short, all the planets except those of our solar system, namely Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. There are billions of exoplanets in the universe, which are very far from our Earth. The possibility of extraterrestrial life somewhere in the universe is therefore stronger than ever. Since the discovery of exoplanets, scientists have been trying to find another Earth, or at least an exoplanet that would meet all the conditions for the development of life. These criteria were modeled on what we know, the development of life on Earth. For an exoplanet to be a potential candidate for the search for extraterrestrial life, it must first be rocky like the Earth, and not gaseous like Jupiter. It must have water in liquid form on its surface, since water is the basis of life. Why in liquid form? Because liquid water allows molecules to meet and interact to create life. This is not the case with frozen water, for example. Finding an exoplanet that harbors water in liquid form is not so easy. This planet must have a mass close to that of the Earth. If it is too massive, its gravity will attract all the surrounding gases, and we will have a gaseous planet. This is why the most massive planets in our solar system, Jupiter, Saturn, Uranus, and Neptune, are gaseous and not rocky. But if we are in the presence of an exoplanet that is not massive enough, its gravity will be too weak to retain its atmosphere. However, the presence of an atmosphere is another criterion for the development of life. Without an atmosphere, water in liquid form would evaporate instantly. For an exoplanet to harbor water in liquid form, it must also have a moderate surface temperature. This means that it must be neither too hot, otherwise the water would evaporate, nor too cold, otherwise the water would freeze. It must therefore be in what astronomers call the habitable zone of its star, i.e., the zone where the temperature allows the presence of water in liquid form. K2-18b is indeed located in the habitable zone of its star, neither too close nor too far. Earlier in this trip, we talked about its equilibrium temperature, which is minus 23 degrees Celsius, or minus 9.4 degrees Fahrenheit. This is very close to the Earth's equilibrium temperature of minus 18 degrees Celsius, or minus 0.4 degrees Fahrenheit. In practical terms, K2-18b orbits closer to its star than we do to the Sun. But let's not forget that its star is a red dwarf, smaller and colder than our Sun, which is a yellow dwarf. K2-18b receives about the same amount of energy as we receive from the Sun. According to the analyses, it would receive about 1,500 watts per square meters, while we receive from the Sun 1,370 watts per square meters. However, scientists do not get carried away. It is not because K2-18b is located in the habitable zone of its star that it is necessarily inhabited. The appearance of life on Earth was the result of multiple factors, not only of a favorable temperature. It is possible that K2-18b harbors living single-celled microbes and bacteria, but depending on the composition of its atmosphere, it may not be able to harbor more complex creatures. This has been established for many exoplanets that have been discovered. They were located at the right distance from their star, in the habitable zone, but their atmosphere saturated with toxic gases makes them unsuitable for the emergence of complex life. What convinced scientists that K2-18b could prove interesting for the search for alien life was the discovery of water vapor on this exoplanet in 2019. Two independent studies, combining data from the Kepler, Hubble, and Spitzer telescopes, have concluded that the atmosphere of K2-18b contains significant amounts of water vapor, which is unprecedented for an exoplanet located in the habitable zone of its star. In other words, this is the first exoplanet found that combines being in the habitable zone of its star with evidence in its atmosphere of liquid water. How did scientists discover water vapor in the atmosphere of an exoplanet located more than 100 light-years from our planet? The first team used data from the Hubble telescope's wide field camera and used an algorithm to process the data. They identified the molecular signature of water in the atmosphere of K2-18b. The second team used data acquired during 3 years by the Hubble, Spitzer, and Kepler satellites to analyze 8 transits of K2-18b in front of its star. In particular, they observed the spectra of the starlight passing through the atmosphere of the planet during these 8 transits. They found that the atmosphere of K2-18b is rich in hydrogen and helium, with a high concentration of water vapor, probably between 20% and 50%. According to astrophysicists, detecting water molecules is very common on gas giants like Jupiter, but rarer in the atmosphere of rocky planets like Earth, especially when they are in the habitable zone. Until now, scientists had only deduced from numerical models the presence of water molecules in the atmosphere of Proxima B, which orbits Proxima Centauri, the closest star to the Sun that we observed on our way here earlier. And that's it. The direct detection of water molecules in the atmosphere of the rocky exoplanet K2-18b is thus a new fact, especially since it is quite possible that the detected water could form rain droplets, or even an ocean on the surface of K2-18b. As a reminder, water had already been detected in exoplanets, but they were not in the habitable zone. This is the case, for example, of HD 209458b, WASP 12b, WASP 17b, and WASP 19b. The astrophysicists recalled that the presence of water in the atmosphere of K2-18b does not necessarily mean that it is inhabited or even habitable. Many questions still remain, including how much water vapor is present in the atmosphere, and whether it is accompanied by traces of organic chemistry, such as oxygen and ozone. All that is known is that, like Earth and Venus, K2-18b is probably composed of silicates as a rocky planet, and that water may not be present in liquid form, but as ice. Scientists expect a lot from the observation of K2-18b with the James Webb Space Telescope, launched in December 2021. More powerful than Hubble, it will perhaps be able to tell us more about the precise composition of the atmosphere of K2-18b. If these discoveries have excited a large part of the scientific community, there are still some gray areas. First of all, K2-18b is between 6 and 10 times the mass of the Earth, with a radius of 2.3 that of the Earth. With this radius, its density seems far too low to be a rocky planet. If K2-18b is indeed rocky, then it would be composed largely of so-called volatile constituents, which would form a fluid envelope, such as molecular hydrogen, helium, and water. This is why K2-18b is often referred to as mini-Neptune. Indeed, Neptune has no solid surface. It is in fact composed of a solid core covered by a warm and dense layer of water and liquid ammonia, and its atmosphere is made of hydrogen and helium. In addition, for water to be present in liquid form on K2-18b, other factors would have to be present. The presence of water molecules in the atmosphere of the exoplanet does not mean that it is present in liquid form. It could very well be in the form of ice. To be sure that the water present on the surface of K2-18b is indeed liquid, it would be necessary to verify the water content of the planet, the composition of the atmosphere, the rotation of the planet, the existence or not of a solid surface. We still don't know if K2-18b looks like a super-Earth or a mini-Neptune, which would be inhospitable. Some scenarios even make it an ocean planet with liquid water under the atmosphere and temperature and pressure conditions close to those of our oceans on Earth. There is one more thing. Is K2-18b really located in the habitable zone of its star? We tend to rely on what we know. So by comparing K2-18b and the Earth, especially their equilibrium temperatures, it seems that yes. But let's not forget that K2-18 is a red dwarf, very different from the Sun, which is a yellow dwarf. The spectrum of K2-18 is more efficient to heat an atmosphere than that of the Sun. If we were to place the Earth at the same location as K2-18b, it is likely that the oceans would evaporate. Instead of reflecting 30% of the incident energy, the Earth would reflect only 10%. For K2-18b to be habitable, it would have to rotate synchronously with its star, i.e., it would always show the same face to K2-18, which would allow thick clouds to form on the exposed half. This would give a habitable climate. These questions are still being studied by astrophysicists, who are waiting for more powerful telescopes like James Webb to confirm or refute their hypotheses. The observations of James Webb could also enlighten us on the difference between methane and water vapor, which remains unclear. Recently, a study conducted by Lesia researchers has shown that the absorption observed by Hubble during the 8 transits of the planet in front of its star could in fact be due to methane. Methane is found in abundance in the atmosphere of temperate mini-Neptunes. Methane is certainly less abundant than water vapor, but the two can be easily confused. The instruments on board James Webb will probably be able to tell us more. Let's assume that K2-18b is indeed home to life. You wonder then what life would be like on this planet located thousands of billions of kilometers away and miles from us. The notion of a habitable zone remains very relative. By definition, it is, as you know, the distance at which a planet, in relation to its star, could potentially harbor liquid water on its surface. The distance varies according to the radiation of the star. For a red dwarf, the zone of habitability is closer than for a yellow dwarf like the Sun, because a red dwarf is colder, smaller, and less luminous than a yellow dwarf. K2-18b is thus located closer to its star than we are to the Sun. Given this proximity, there is a strong chance that K2-18b is in synchronous rotation with its star. On this planet, there would be no nights or seasons. Living beings would be grouped on the day side, the one that is always facing the Sun, while the night side, too cold, would be uninhabited. The red dwarf, as its name indicates, emits a red radiation, unlike our Sun, which emits a yellow radiation. The living beings on K2-18b would thus see in the sky a red star, with a disk certainly larger than the solar disk, since K2-18b is closer to its star than we are to the Sun. The gravity on K2-18b is 37% greater than on Earth. Thus, the development of life on this planet would have adapted to this stronger gravity, giving forms of plants and animals much more imposing than what we can know here on Earth. The living beings would have more strength compared to us, and would need more energy to feed themselves. Obviously, we would not find the same plants on this planet. Studies have shown that plants are indeed sensitive to red light because they have a photoreceptor for red light, a blue-green pigment called phytochrome, which is found in plant cells. Plants grown under red light are larger and taller, with many branches. Red light could also influence the color and flavor of plants. Instead of being green, K2-18b plants would be black in order to better absorb light from the K2-18 star. Red dwarfs are known for their frequent violent eruptions. The Sun also has eruptions, but much less violent than that of red dwarfs. We are also protected by the Earth's magnetic field. On the other hand, the eruptions of red dwarfs would be capable of tearing the atmosphere of the planets around, especially since habitable planets around red dwarfs are much closer to their star than habitable planets around a yellow dwarf like Earth. So even flares similar to those of our Sun could affect planets like K2-18b more. The researchers then wondered if, because of these frequent flares, exoplanets around red dwarfs might be too hostile for the development of life. Not only could a single eruption of the red dwarf K2-18 damage the atmosphere of K2-18b, but also, according to some researchers, there could be a cumulative effect. In other words, the more eruptions there would be, the more the atmosphere would be torn apart. Thus, even the weak eruptions, which seem to be the most frequent, would present a danger. However, it all depends on the composition of the atmosphere, which scientists have not yet been able to determine precisely with respect to K2-18b. It could thus be difficult to find habitable land around red dwarfs. Indeed, a planet of mass equivalent to ours or higher has great chances to keep throughout its evolution because of its gravity, a thick atmosphere. Also, in these conditions where the greenhouse effect is enormous, the possibility that water could remain in a liquid state evaporates. But all is not lost. For researchers, the conditions for a form of life would be more favorable on the surface of worlds less massive than the Earth. Planets similar to Mars, called exomars, which do not retain their atmosphere well, could be good candidates. The good news is that these small balls of rock are probably much more numerous than the larger, more massive planets. If life were possible on K2-18b, the life expectancy of a species could be much greater than that of species on Earth. Because red dwarfs evolve very slowly, much slower than our Sun, which will eventually turn into a red giant, swallowing the Earth in about 5 billion years. A red dwarf, therefore, leaves much more time than a yellow dwarf for life to develop on the planets that orbit it. At the moment, the latest data suggests that water vapor makes up between 0.01% and 50% of the atmosphere of K2-18b. With such a large range, it is difficult to characterize the exoplanet. It could be completely covered with water, or on the contrary, be a world similar to ours, with lakes and oceans with many exposed lands. What if K2-18b was an ocean planet? If so, the planet would be home to aquatic species, surely different from those found in our oceans. This extraterrestrial ocean could be deep and dense in such a way that even at high temperatures, the pressure would turn the deep water into ice. The immense pressures in these deep ocean regions could lead to the formation of a mantle of exotic ice forms. This ice would not necessarily be as cold as conventional ice. If the planet is close enough to its star, as is the case with K2-18b, and the temperature and pressure at its surface are high enough for the water to reach its boiling point, the water would become a supercritical fluid and would not have a well-defined surface. But according to the latest data, the surface temperature on this planet is between -73 degrees Celsius and +47 degrees Celsius, i.e., between -99.4 degrees Fahrenheit and +116.6 degrees Fahrenheit. Even if the temperature is still uncertain, it is not high enough for the water to reach the boiling point. If K2-18b is indeed dominated by water, the atmosphere may be much thicker than Earth's and composed largely of water vapor, producing a very strong greenhouse effect. The problem? Such a planet would have to be small enough not to be able to hold a too thick envelope of hydrogen and helium. Otherwise, they would rather form a hotter version of an ice giant, like Uranus and Neptune, making any form of life impossible. However, K2-18b is a super-Earth and could very well have evolved as a hot Neptune, but its proximity to its central star could save it. Indeed, as K2-18b is close enough to its Sun, it could be stripped of its light elements by the solar flares of the red dwarf, thus preventing the formation of a thick atmosphere. So there could well be stable oceans on K2-18b. Even if the oceans of K2-18b are of different composition than ours, this does not mean that life would be impossible there. On the contrary, it would simply be another form of life. We have found organisms on Earth that are capable of developing in the Dead Sea. The tardigrade is a good example of an ultra-resistant animal species. 1,000 tardigrades were sent to the Moon via a space probe in 2019, and since then these animals have survived perfectly well in this inhospitable environment. The tardigrade is an animal with 8 legs, which measures only 1 millimeter, and which can resist to extreme environments. It survives temperatures between -273 degrees Celsius and +340 degrees Celsius, i.e., between -460 degrees Fahrenheit and 644 degrees Fahrenheit. It is 11,000 times more resistant than humankind to X-rays. it survives pressures 4 times higher than the pressure of the deepest part of the ocean, but also the lack of oxygen, dehydration, alcohol, toxic products. In addition, it can reproduce alone. To adapt in this way to such extreme environments, it changes its mode of functioning, and in particular, resorts to cryptobiosis, a state in which it is almost dead. It curls up, it empties itself of its water, which it replaces with a sugar, and it reduces its metabolic process to 0.01% of normal. It can rehydrate and wake up decades later. Outside of cryptobiosis, its lifespan is 1 to 3 years. We could therefore find ultra-resistant animals on K2-18b, whether it is an ocean planet or a rocky planet, which would resist solar flares, and perhaps even the temperatures and lack of luminosity of the night part. The example of the tardigrade shows that we should not underestimate the capacities of animal species. Now, let's suppose that K2-18b could harbor life and that there are aliens on this exoplanet. After all, why not? And if so, could we communicate with them? The participatory project, Stahaya Beyond, which was born in Uzbekistan, aims to send musical tracks to extraterrestrials. The goal is to transform a selection of local and international music into binary code so that it can be sent into space via a UK satellite radio station in order to reach K2-18b, the best candidate to date for the presence of extraterrestrial life. However, although K2-18b is not the most distant exoplanet from us, it would take 124 years for the extraterrestrials to receive the message. The earliest we could get an answer would be 248 years. This project is an opportunity to ask many questions. What will we do if we come into contact with the extraterrestrials? How will we communicate? And especially, how will we understand each other, since they will not speak our language? This also brings us back to the question, are we alone in the universe? A question that astronomers have been asking for centuries, and to which we are not close to finding an answer. So, does K2-18b harbor life? If it does harbor life, is it an advanced extraterrestrial civilization with which we can make contact? Terrestrial or aquatic animals whose existence we do not suspect? Or plant or bacterial life? The questions about this exoplanet, more massive than the Earth, but which resembles it very much, remain numerous. Astrophysicists hope to learn more about it, thanks to the very advanced telescopes that have recently been deployed, in particular the James Webb, which has powerful instruments that allow us to see in the middle and far infrared. In any case, you now know that although there is probably no planet exactly like Earth in the universe, there are planets that are similar in some respects, and could possibly harbor, or have harbored, life. K2-18b is one of them, and it is one of the exoplanets in which astronomers are most hopeful. At least, until the next discovery.